All right, so definition of an inverse. So this is definitely like all up until like the last example in this section is pre-cal review. What is an inverse? An inverse is really, it flips across the axis y equals x. But by definition, f of function g is the inverse function of f if composition. If you remember, the way to prove that something is an inverse is to do the composition. And if when you take the composition it equals x, they're inverses of each other. And so that's the definition there. So are these inverses? Well, how do you tell? You literally just plug one in the other. So f of g of x, I would say 2, and instead of x cubed, I would say the cubed root of x plus 1 over 2 cubed minus 1. These cubes cancel each other out. So you have 2x plus 1 over 2 minus 1. Your 2's cancel out, and you get x. So yes, these are inverses of each other. Hopefully that is familiar. The existence of an inverse function. Not every function has an inverse function. You can find an inverse relation, I guess, but for it to be an inverse function, it needs to be a one-to-one relationship, right? And so the way you tell if it's a one-to-one relationship, is it a function, would be the vertical line test, right? So if I were to look at this first graph here, vertical line test, yes, that's a function. If I look at this graph, vertical line test, yes, that's a function. So then how do you know if the inverse is a function? You know you can find an inverse, but it is an actual function at that point. And so then you can do a horizontal line test. Yeah, so go this way. Yeah, this guy's going to have a function as its inverse. This guy is not. Because when I flip him, a vertical line test will fail. And so you can use the horizontal line test to tell you if it will fail when you do the inverse. Basically, you're seeing, will the vertical line test fail on the inverse? Well, the way you do that is you do a horizontal line. So, some guidelines for finding the inverse. Hopefully this is also very familiar. First, you determine if it's going to have an inverse. Solve for x as a function of y. So basically what you're going to do, starting with number 3, switch x and y and solve for y. Define the domain of f to the -1, which is your inverse, to be the range of f, and verify that your composition works. That tells you did it correctly. So basically your range, a domain and range switch places when you have a function, which we did some word problems like this in pre-cal, if you'll remember, and it'll be like, hours and income was the original function. Well, the inverse, the hours are no longer the x, the hours are going to be the y, and the income is no longer going to be the y, the income is now going to be the x. And so basically the domain and range just switch places. So this one is finding the inverse. Well, the first thing I'm going to do is I'm going to switch my x with my y. So instead of y equals the square root of 2x minus 3, I'm going to have x equals the square root of 2y minus 3. I am going to get rid of that square root by taking the square of both sides. So x squared equals 2y minus 3. Add my 3 over. And then divide by 2. So I have y equals x squared plus 3 over 2. And you want to rewrite that with your little notation. The inverse of f is x squared plus 3 over 2. I'm going to make that a little bit prettier of an x squared. And so we have our function. And you can check yourself by just saying f of inverse. You should get x. If you don't get x, you did something wrong. Either in your original or in your checking, you did something wrong. But you can check these to make sure that you did that inverse correctly. So the function that they give us, f of x equals sine of x, is not a one-to-one on the entire real line. Well, the reason it's not one-to-one, now it's one-to-one one direction, right? Which clearly sine is a function. But the inverse of sine is not going to be a function, because if you look at the graph, of this guy, it's a wave, right? So yeah, we have this, I don't want a box. We have this thing here that goes around, right? And the problem here is that it's one-to-one, one direction, but this is clearly going to fail a horizontal line test, right? We have a problem. And so your trig functions very often will not have a valid inverse. Now, some of them will, right? You have your tangents, right? Because those are just almost like a cubic function is what they kind of look like. And so those will pass a horizontal and a vertical line test. But you have other issues that arise with those. So, all right, let's look at continuity. Continuity and differentiability. So let f be a function whose domain is the interval I. If f has an inverse function, then the following statements are true. If f is continuous, then the inverse is continuous. If it's increasing, then the inverse is going to be increasing. If it's decreasing, it's going to be decreasing. If it's differentiable at c, and that does not equal 0, then your inverse is also differentiable at c. So then let's look at the definition of the derivative of the inverse. All right, so let f be a function. So we have f is our function that's differentiable in the interval I. So we're saying we have a derivative. If f has an inverse, let's say that's g, then g is also differentiable for any x as long as it doesn't equal 0. And here's the kicker. That little button means prime. So the derivative of the inverse is going to be 1 over the composition of the function, the inverse inside of the derivative. Yes, very strange, I know. So the derivative of the inverse at a point is going to be the same thing as the composition of that point in the inverse taken in the derivative of the original function. So they give us an example. So we have this function here, 1/4 x cubed plus x minus 1, which is this darker line here. This is my original function. What is the value of the inverse of x when x is 3? What is the value of the derivative of the inverse of x when x is 3? All right? So notice that f is a 1-to-1, right? So we know this is going to have a inverse and that it will be a function. So then we can just plug it in. All right? So the first thing we're going to look at is the first question. What is the value of the inverse when x equals 3? Well, on the function itself, right, I have the point 2, 3, which tells me, even without a graph, that I will have the point 3, 2, right, in the inverse. Because remember, your domain and range just switch places with inverses. So if I have the value 2, 3, so if f of 2 equals 3, then f prime of 3 will equal 2. That is how that will work, right? So the first question's easy. Well, the inverse at 3 is going to be 2, because I know that the function at 2 is 3, and so I know my domain and range just switch places. And even if they didn't give me the graph, I could figure this one out by just plugging it in. 1/4 of 2 cubed plus 2 minus 1, right? And so I'm going to get 2 plus 2 minus 1 equals 3. So even if I didn't have the graph there, I could figure out what it was at 2, right? If I didn't have the graph at all and didn't know 2, 3 was on there, I could find the inverse and plug in a 3. Either way. All right, so then the next question. What is the value of the derivative of the inverse? What's the value of the derivative of the inverse? Well, according to my definition down here at the bottom of page 336, I need to find out the derivative at the inverse at 3. That's what because they want the derivative of the inverse. So the derivative of the inverse equals this guy. That's what it equals. All right. So then need to first say, well, what is the inside? Well, the inverse at 3 was 2. We've already calculated that. So I need 1 over the derivative at 2. That's what g of 3 is. G of 3 is just my inverse, okay? Well, how do I find the derivative at 2? Well, I just take the derivative. That's an easy derivative to do. What is the derivative? Well, multiply by your exponent, right? So you get 3/4 x squared minus 1, right? That's the derivative. Is that not derivative of f, right?
Is it plus 1 or minus 1?
It's plus 1. Sorry, I jumped. All right, plus 1. So then what do? Plug it in, right? So I have 2 squared, which is 4, right? Then I have 4 over 4 is 1, so 3 plus 1 is 4. So this guy right here is going to be equal to 4. So my answer to what is my inverse derivative at 3, that's going to be 1/4. But if you look here, it says let f of x equal x squared for x greater than or equal to 0. And let the inverse of x equal the square root of x. Show that the slopes of the graph of f and f of -1 are reciprocals at each of the following points. All right? So then how do you find slope? Well, slope is my first derivative at that point, right? Slope is my first derivative at my point. So if I were to take the derivatives of each of those, the derivative then of my function itself is just going to be 2x, right? And the derivative of this guy, right? You can do it 2 ways. You can just straight up take the derivative, x to the 1/2, multiply by 1/2, and then x to the -1/2. So you get 1 over 2 squared of x. Or if you had your numbers, you could just plug it in, right? And so how do I find out that it is the case at 2, 4, and 4, 2? Well, I'm just going to plug it in, right? So I'm just going to plug in the derivative at 2, right? Derivative at 2 is just going to be 4, right? And the inverse's derivative at 4, right, is just going to be square root of 4 is 2, right, 1/4. They're reciprocals of each other, right? So you can just plug it in and show that that's happening. At 3, you have 6, right? And at 9, you have 1/6. So you can see that what happens here is the slopes become inverses of each other, which is true. Like when we did linear functions, you could see that. But with this, you're going to have to find the slope at the point because a linear function has the same slope all the way across. That's not true of regular functions other than linear.